The recording has started. Yeah. So again, thanks for reminding. So yeah. So where did we stop yesterday? Is the start of this definition of optimization problem. So what generally is the problem statement for optimization problem? We have earlier seen what is the connection between optimization and deep learning. So I mean, why do we need to really learn a bit of optimization, or rather brush up the optimization? Some methods of basically iterative optimization that will come in this lecture, hopefully time permitting. So this is the problem statement that minimizing a function of a scalar function of a vector variable, where the scalar function, we told that we generally term it as objective or loss or cost function subject to some constraint. If the constraint is not there, then it is a unconstrained problem. Then we went to this a little more I would say a different class of optimization problem, or just a subclass of optimization problem, which is convex optimization, where these two conditions get added. So the thing is that this function f is a convex function, and this domain of the minimizing variable argument is a convex set. So let us see what do we mean by convex function and convex set. So first let us come to what is convex set. So a set C in Rn is a convex set if for all xy belonging to C, that is for all pairs of points that belongs to C, the line segment connecting x and y, those 2 points, is in C also. So if x and y are 2 points in this set C, then the line segment that connects them, the whole line segment actually belongs to that set C. So that is the definition of convex. If this condition is fulfilled, then the set C is a convex set. Now, how do we express the line segment connecting x and y between? The line segment connecting x and y is this. So it is theta x 1 minus theta y, where theta has this condition. Theta belongs to 0, 1, both included. So when it is 0, then of course you will see that it is y. This combination, this is called a convex combination of between x and y. So a convex combination between x and y is defined as this. There are other combinations. It's a class of linear combination, right? So it's ultimately a linear combination, but it's a subset of the linear combinations. There are conic combinations, etc. They are there. So convex definition is that when you combine, the sum of the coefficients should be 1, and each of the coefficient value should be between 0 and 1. So this also satisfies in this case. So theta and 1 minus theta, the sum is 1, and both are between 0 and 1. Since theta is between 0 and 1, both included. So when theta is 0, you see that the point is y. When theta is 1, then the point is x. So how, just to convince you that yes, for theta, any theta between 0 and 1, for 0 and 1, we have seen that one point is x, which is for theta is equal to 1. Yeah, and another point is y when theta is 0. So what happens, whether it really happens that between when theta is between 0 and 1, this combination is a point on the straight line connecting x and y. So it's an intuitive sort of justification that I am trying to show for a two-dimensional case. So let's say these are the same 2 points, x and y, as like this and this. Then so theta x plus 1 minus theta y, this I can write it in this form, right? So y and then theta x minus y. So it's like the point y is there, and then you are adding to it a portion of x minus y. So what is y? This is y. What is x minus y? It is this, because this is minus y. So x minus y, just simple vector addition. Okay. So if you now put theta is equal to 0, of course, this comes y. So this x minus y, this thing multiplied with theta, it is 0. Now, when theta is 1, you know from here that ultimately you will get x, right? From here, when theta is 1. So let us see if we put theta is 1, what happens. So if we put theta is 1, that means this vector and this vector both get added, and this gets added to this point x, right? So I mean, this is just from the geometry. Then what happens is, if theta is any value between 0 and 1, right? So we see that okay, I mean, these, how to do this undo, I'm not totally sure. Somewhere, okay, clear pen markings. Okay, that's better. So okay, so what happens is this theta, when I multiply, so any value between 0 and 1, so this xy gets multiplied, sorry, x minus y gets multiplied with theta, so theta into x minus y. So now you have to basically add y, that is this, and theta times x minus y, which is this, which geometrically is this. So this is basically just again a geometric intuition of to convince you that okay, yes, this combination actually is a point on the connecting is a point on the line connecting x and y. Now some examples of convex sets. I mean, again, from geometry you can see that if you try to find any 2 points here, it will be inside. I mean, the straight line connecting those 2 points will be inside here. It is, if you connect here, everything, circle, these conic pi, etc. Now this is not a convex set, because yeah, you can find such points here that if you connect the straight line, this portion is outside the set. So this is not a convex set. Similarly, set is a collection of elements. So this is a set, but not a convex set, because if you just try to connect these 2 points, I mean, this whole line segment is outside the set. So this is just some basics of convex set. What is the definition, some examples, some geometric intuition, and so on. Now, we have seen here that it has, okay, the convex optimization problem has not only convex set, but convex function. So what is a convex function? Let us see. Okay, so convex function's definition is a function f coming from Rn to R is a convex function if its domain, first of all, that is this, whatever is the domain, is a convex set. So I should have really written not Rn, but any n-dimensional space. So it's not the whole Rn. I mean, it may not. It's a convex function, convex set, and for all xy in domain F, sorry, where it is, yeah. So all xy belonging to domain F and theta in 0 and 1, we have this. If this relation is satisfied, then it is a convex function. Now, what does this relation tell? So first of all, that if I mean, the domain of F is a convex set. So any 2 points, if you take x and y, the point connecting, any point on the line connecting these 2 points will be also in that. Let me go ahead. Okay, so what is a convex function? So convex, okay, sorry, here. Yeah, so convex function is a convex function if its domain is a convex set, and for all xy belonging to domain F and theta this, we have this relation. Now, what is the relation? What does the relation tell? First of all, I mean, the definition of convex function says that the domain is a convex set, right? And we have seen in the definition of convex set that any two, I mean, if 2 point belongs to convex set, the line say, connecting these 2 points also belongs to the same convex set. And we have seen that this is any point on the line connecting the 2 points in that convex set, that is x and y. I'm telling only about the one which is inside this bracket, this theta x plus 1 minus theta y, right? So what does it tell is that if you if f is a convex function, then if you evaluate the function on a convex combination of 2 points, And if you convexly combine the two points function value, that is theta fx and 1 minus theta fy. So here theta x plus 1 minus theta y, for that you are taking the function f or evaluating the function f on that point, which is, suppose z is this theta x 1 minus theta y. So what is f of theta x into 1 minus theta y? This is this red point. And what is this? This is theta fx. So what is fx? Fx is, so x is this, so fx is this, y is this, so fy is this. So what is theta fx plus 1 minus theta fy? It is this. So any point on the line connecting this x and y. Okay, so I have, what I have drawn is okay, it happened to be just vertically above, I mean this black dot is just vertically above this red dot. It may not always happen. It may be that the theta value is such that x and z, when you combine, sorry, x and y, when you combine, it comes here, but when you combine fx and fy, it might come here. So that's just something that when I drew, I did not notice. So what geometrically it is telling is that if it is a convex function, and convex function, you can think of it as a bowl shaped function. So it's actually literally looking like a convex surface. So for such a convex function, it always happens that if you take a convex combination of the points and you basically evaluate the function, it is always less than the convex combination of the functions evaluated at the individual points. Are the things clear here? Like geometric intuition of what is convex?
Sir, in this case, in this equation, sir, the right hand side, the thetas can be different, right? In left hand side or right hand side?
No, I mean
the point you explained.
So thetas can be different means, I mean theta can be any value between 0 and 1.
No, sir, like you have mentioned, like in right hand side you have written theta, and left hand side also you have mentioned the parameter with theta. I'm saying yes, that they can be different, take different.
No, in the definition or in the equation, when suppose you are asked to find whether a function is convex, so in that case, of course, for the same theta you have to do it. But the theta, I mean the same theta, suppose the theta value is 0.5. Okay. So that same, or 0.5 is a bad value, maybe 0.4. So 0.4, then the same theta will appear here and here to check whether the function is a convex function. But that 0.4 can be 0.6, 0.7, etc. But both sides have to reflect that. That is the definition. Okay.
Okay.
Yeah. Okay. Let me go ahead with the example, and then we will stop for some questions. So this is one example. All norms are convex functions. So how to prove that? So norm is given by these vertical bars, right? So if norm is a basically convex function, if you need to prove it, then you need to prove that the norm of theta x plus 1 minus theta y, this is less than norm of or theta times norm of x plus 1 minus theta times norm of y. That's what you need to prove, and that's what we have tried to prove here. Very simple proof. It uses the triangle inequality first. So this is the triangle inequality tells that this thing is less than, the left hand side is less than theta, norm of theta x plus norm of 1 minus theta y. And then since theta is a positive number, actually it is between 0 and 1, or rather non-negative number, we can take out theta out of it. The general rule is that you take the absolute value of theta, right? But the absolute value is equal to the value of theta, because theta is range is 0 and 1. So we have proved this. So norms are convex functions. So we can very simply prove that. Now, alternative definition of convexity for differentiable functions. So this is for differentiable functions. So that was a definition, just the standard definition of functions, convex functions. Now, it's an alternative definition. That means that it is a property that is a necessary and sufficient. So that means we can prove it from both sides. If this is true, then it is a convex function, and if convex function, then this is also true. So what does it say? It is also named as first order characterization. So again, f is a differentiable function. So but the thing is that it has to be differentiable. The function has to be differentiable. There may be convex functions which are not differentiable, but those are like very typical complex examples. I'm not going to that. Whose domain f is convex, then f is convex if and only if fy is greater than equal to fx plus inner product between grad fx and y minus x, where x and y belong to domain f, and that is true for all xy belong to the domain of f. Now the thing is that this is a notation that I have used. I mean, I have taken from that book, and I think it is taken from Boyd and van der Waage. They use this as the inner product. So it just tells that this is grad f x, which is a vector, you know, by this time, transpose y minus x, right? So this. So let us see if, I mean, I will try to prove one direction of it. The other direction is there in the slide. Just to save some time, I will try to not go through it. If you have any problem there, you will, you can. Yeah, I have one thing. I have added all of you to Piazza. Just check your mail. I have sent the invitation mail to both Gmail and both the non-institute ID email and the institute email. So if you have not received it, check spam. I saw many people have basically enrolled. So if you have any problem on that part, please let me know. Okay. So let us go to this proof of part one. What is part one? Proof part one means one direction. That is, if this equation is true, then from this equation, how can we go from this definition, right? So let us see. So given that equation fy greater than equal to this, let us consider xy is in domain F and theta is between 0 and 1, because that is the condition, right? Theta is between 0 and 1 because we need it to convexly combine two points, which is in domain F, and domain F is convex, it is said. So remember this, that domain F is convex. I mean, this is the theorem that domain F has to be convex and this has to be met. So if xy both belong to domain F and if theta is between 0 1, then this combination is also inside this set, this domain F, because it's a convex combination. Just note that I have taken, for some mathematical convenience later, that's just the algebraic manipulation gets better. That's 1 minus theta here and theta here. So still it is a convex combination. Now by equation 1, that is this, I mean this, since z is also a point in the same set, so x z we can take, and since we are trying to prove from here to the definition, this equation is true, we have assumed. So this equation applies to xz. So fx greater than fz and inner product of fz x minus z. Similarly between yz. Okay, so now we have just termed these as 2 and 3. Now you can like try to guess where I am going, because for from the definition, what I have to do is f of say 1 minus theta x plus theta y, that needs to be less than equal to theta. Oh, sorry, I have taken 1 minus theta here. Again, undo, I am not sure. 1 minus theta fx and plus theta fy, right? So this is what I think we are trying to go. So we have got fx and fy. Here is fx and here is fy. So what will you do? You will multiply with 1 minus theta and theta respectively, this equation and this equation, right? So that's what I have done. So multiplying equation 2 with 1 minus theta, that is what the equation that contains fx on the left hand side, and equation 3 with theta, that is the equation that contains y on the left hand side. So this is one, right? So this and this, right? Because yeah, if you multiply fx with 1 minus theta, you get this, and if you multiply theta with fy, you get this. So now what you will be doing, the next natural step is just summing them, right? So you are summing these two equations, So left hand side, this is the right hand side. I'm just copying this equation on the next slide. So what do you get here? So you want to prove that this is greater than. So I mean, just to remind you, this is what we generally keep it on the right hand side on the definition. So, but just so that you don't get confused, I'm telling it explicitly that this is the one which needs to be greater than your f of 1 minus sorry, yeah, Deepak, can you mute yourself? Otherwise, yeah, I'm Deepak Chaudhary. Thanks. So yeah, so this thing needs to be greater than f of 1 minus theta x plus theta y, right? Now, if you see it here, okay, let me go ahead with one more line, and then it will be much more clear. Okay, again, I have to clear the annotation. Okay, so I'm just expanding this, and you see that this theta fz and theta fz gets cancelled. So even if I ignore whatever there is there on the right hand side, you see z is what? What is z's definition? So z's definition is here 1 minus theta x into plus theta y, right?
Hello, sir.
Yeah, yeah.
Sir, I have to say something.
Yeah, sure. Yeah.
Sir, you're moving too fast. We are not understanding anything. You pre-assume things like we know these math things early, but we are not getting anything. You're moving too fast.
Yeah, see, this is just brush up optimization. I mean, that is the prerequisite. Have you done machine learning?
No, sir.
Yeah, so that then you need to, I mean, we have to move fast, otherwise we will not go into deep learning, right? I know that I'm moving fast, and that's why I think the recording will help. There will be I mean, have you enrolled in Piazza?
Yes, sir.
Yeah, so if you have any questions, please post there. And it's not that everything will be, I mean, it's not possible, right? Everything will be explained in the class. So you have to put in your effort also. I will try to go slow, but that will mean that maybe we will just complete the semester just by without ever reaching the reply, right? So that's why I put the prerequisite. So you are a master student. I mean, does not it require a prerequisite to be satisfied to enroll, or what? I mean, you are a
sir, but even in the machine learning course, I don't think this was taught.
See, machine learning's prerequisite is basic maths, right? So optimization, then probability statistics. So that's why these parts I have to go first, because you then see this is advanced graduate level course, right? So you have to put in your effort also, because otherwise the deep learning part I am not will be able to go, right? But yeah, if required, this Tuesday, I mean, this last Tuesday, I did not attend the office hour, but yeah, this Tuesday I can be there. So you know the office hours, right? Can anybody tell when it is? I have announced it.
Tuesday from 6 p.m.
Yes, Tuesday 6 p.m. Same link, right? Same Zoom link. Okay. And you talk to your friends, because maybe that these things are very trivial. I mean, to some of them, not maybe to you. So maybe they can also help. Otherwise, I mean, again, for a but anyway, where is the problem? Where is the part where you did not get? Have you looked into the slide? I have told that the slides are up, so you have to come prepared, right? It's, I mean, how can I tell it? The slides are up, the videos are there, you have to give in time. How many courses are you taking in this semester? Arav? Yeah, Arav.
Yes, sir. 9 courses.
9 courses. You are in which, oh man, 9 courses. Which year and which semester are you in?
So 6th semester.
Oh God, 9 courses you
So
have
for
to take.
all CS department students, I think 9 courses are compulsory.
I mean, 9 courses you have to take.
Yes, sir.
Oh God, 9 courses. How can you give time? I mean, is it like this everywhere? I mean, all IITs, do you know? Do you have any idea? I mean, 9 courses is like inhuman. I don't know. I mean, I should not say these things, but 9 courses. I mean, I wouldn't have coped with 9 courses. Anyway, but yeah, I mean, don't worry about it. I mean, probably you take feedback from your seniors that, I mean, at least as far as assignment homeworks are concerned, this is not a very loaded course. I want to give
very fast. Actually, we cannot comprehend things.
Yeah, because this is the brush up part, right? This is only the second week, right? So if I don't go fast, how can I go to the more interesting parts, right? So you need to give time. I know that, I mean, if all the 9 semester teachers, I mean 9 course teachers ask you to give time, it is I mean beyond imagination. But again, I think we can discuss these things in office hours. What strategies can be taken, right? So otherwise, I mean, these things, I mean, I can probably take one class on it, like how to basically go about this, right? Maybe it is a 6th semester, right? Okay. Probably, and if you are a BTech student, yeah, this is the time to take this course. Yeah, otherwise, I mean, for a dual degree student, I would have said that maybe you can take it on the 8th semester. Anyway, let us go ahead with it.
Hello?
Yeah.
Sir, I was there in the meeting previously, but someone removed me from this meeting, and then I was having difficulty joining it.
That should not be the case. But you I mean, I at least did not remove.
So someone removed me from this meeting, and then I was having problems. I don't know. I joined from a different device.
Okay.
So I'm from this course. I'm an MTech student.
Okay, but yeah, I did not remove. I don't know how it happened.
Okay.
Mhm. Anyway, so let us go ahead. Let us go ahead and yeah, please do come on Tuesdays office hours. Okay. Okay. So yeah. So we see that we are getting this as the left hand side and this as one term as right hand side, and these are some additional terms. Now, if you just ignore this term for the time being, these additional terms, what is Z? So Z is your 1 minus theta times x plus theta y. So this is telling you what we wanted, where we wanted to reach. So 1 minus theta times fx plus theta times fy is greater than equal to f of 1 minus theta x plus theta y. So we now see the strategy to take, that we need to show that this part is 0. So let us go ahead. How can we show that? So this is just I'm getting rid of these two like the cancel terms. Now what is happening? This is an inner product between this and this, and sorry, yeah. So let me come. How did I come from here to here? So this is an inner product between this, and the whole thing is multiplied with a scalar. So you can very well write it as an inner product of this thing and this thing multiplied with this thing. Is that clear? Right? So that thing you are writing. So this thing is coming here. This and this multiplied are coming here. Similarly, this thing is coming here, and this multiplied are coming here. So these are the two terms. Just I have written it in this form, right? Now, see what are okay. Again, I need to clear this notation, otherwise it is becoming Now you see what, just focus on this term and this term. This and these are common in the inner product, right? So it is like this transpose, say, A where I am denoting this as A, plus the same thing transpose B, where I'm denoting this as B, right? These are all vectors. So how can you write it? Can you write this? That's exactly what I have done, right? So if Z transpose this to this plus this, which is A and B, right? Hopefully things are now a bit slower. Anyway, let us go ahead. So I hope this is clear. Okay, again, I have to. Okay, now this is 0. Now, why is this 0? You can basically think what is the strategy to take. So you just put the value of Z, right? So that's what I have done. So J, okay, first of all, I'm just expanding this. So I need to prove that this is 0. So 1 minus theta into x, so 1 minus theta into x, 1 minus theta into z, this, then theta y is theta y, theta z is theta z, right? Now this you are expanding this part, this is z plus theta z, theta y minus theta z, right? So these two gets cancelled. So 1 minus theta x, this theta y, this negative z is here, and then this whole part is your z. So what it becomes is z minus z is 0. So this is just algebra. I hope, I mean, it may not be that you get it from the slide at this point. Just sit in a quiet room, just give 10 minutes. Nothing more. 10 minutes on what I have told. I mean, I have told probably for 20-25 minutes. 10 minutes, I am confident you will get it. Okay. So this is 0. So this whole thing is just fz, and fz is this. So we have proved that this is greater than this, which is the definition of convex function. So I thought that I will complete it by 12:20. Anyway, so proof of this part 2, that is coming from this to the other part. I'm leaving it as an exercise or kind of self-reading. I will not have time to go through, but the slide is very good. You just go through it. Before I go to the gradient descent discussion, if there is any question on the first part, that is the proof 1 or the definition of convex function or convex set, please shoot away.
Sir, can you please tell some reference for like basic
This
maths?
is so for this best reference is Boyd and van der Waage. So Stephen Boyd has very good lectures from Stanford University, at least till this part, right? Next part, probably 2-3 slides. I don't remember where from I take it. I mean, I took it, I remember it's actually from the linear algebra course that I took in my PhD days, the next probably 3 slides. But then everything is there in the deep learning book, chapter 8. Okay, after like 2-3 slides of this. The thing that I covered till now, this convex function definition, etc. The very good book is Boyd and van der Waage. So Stephen Boyd's book. So I mean, if you are interested, if you want to know more about convex optimization, there are 20 lectures which is there from eternity. I mean, I know he is probably taking this course from 1984 even. Stephen Boyd. So the Stanford, one of the earliest Stanford online series came on that lecture. So if you just Google Stephen Boyd convex optimization, you will see it. Just maybe initial 2-3 lectures would be fine. Just so that I mean it raises your interest. So that's the best reference. You see how many views of that lectures have been. Any other question? Okay, if not, then let us go ahead with this gradient descent. Okay.
Sir,
yeah.
One small question. So in the first definition of the convex function, I think it was intuitively clear that that whenever we take a point which is joining this convex set, the effects, the value of that, the value of the function evaluated at that point will always be less than the convex set value. So effectively, it gives us a single minima. I mean, if we explain.
Exactly.
But so the second part, I mean, of the convex function, I mean, the second formula, is there a way to intuitively understand that or derive a
yes
from that?
I deliberately did not go into that, but since you asked, let me try to give that. So this is basically, this is, okay, let me take it. So this is a linear approximation of a function. So what we mean by this is, you see, this is fx plus this, that is this transpose y minus x. Now, can you tell me where have you seen it? I think if I'm giving you a hint, it's in a series. It's say first two term of a series.
Taylor series.
Right. Taylor series. So this is the Taylor series for multiple variables. So how does it come, or how to basically remember it? It is basically in Taylor series, what do you get? Say x plus h, f of x plus h is, when it is scalar, that fx, just tell me whether I'm writing it right. So hf dash x plus h square by factorial 2 f double dash x and so on, right? Where dash x means single derivative, double dash x means double derivative, and so on. So when you translate it to your multiple variables, these products get replaced with matrix or vector product. So particularly this term is h transpose grad f of x. So similarly like this. So this is the h, you can think, okay, and this is the grad f x. This particular term, or h square by factorial 2. So factorial 2 is like 2, so it will be half h transpose Hessian of fx h. I think I'm writing it right. So, but we don't say consider these things. Just the first two term, if I take, it's a linear approximation of the function. What does it mean? That suppose you have any arbitrary function like this. This is the xy. So if you are trying to find this two term at this point, at this x, you are actually getting a straight line like this. So what this equation tells, that if it is a convex function like this, if you take this linear approximation at any point, all the function value of that convex function will be greater than all the points in this straight line, or greater than or equal to. So it's not strict greater than. So that is the geometric intuition. I'm not sure whether this makes sense, because if you draw this, then you can see that from that you will also reach minima. I don't know, I mean, if that is the question that I am getting, but at least this is the geometric intuition of this form of the equation. Yeah, okay,
got it, sir. Thank you.
Thanks. Okay, any other questions? These are very interesting stuffs. I mean, if you find time, please go ahead and basically, I mean, I don't know much of it, frankly speaking, but yeah, these are some of the things that I mean, I just studied and just needed for my research and this understanding some of the stuffs, literature in deep learning. In deep learning, the thing is that mostly the objective functions are mostly non-convex, highly non-convex. But these analyses that we are doing a little bit, I'm just getting you started. So these can be applied to these locally convex regions. So any highly non-convex objective function can be thought of locally convex. And what till now we do with this gradient-based optimization techniques, we just try to find a minima which is local, which is a local minimum. So maybe that's where these evolutionary methods, gradient-free methods can help. That is what the thought was for most of the many researchers. But yeah, I mean, it has not reached its potential, that gradient-free algorithm still now. Okay. Any other question? Okay, let me quickly go ahead and see how can I, or which are the things that I can cover. Okay, yeah. So yeah, so gradient descent. So we let me go to, or basically I think, yeah, that is what. Yeah. Start with one of the very basic gradient based algorithm that we all use, maybe used in machine learning also, just to give you an intuition how does it come. Okay, so the problem that we are interested is, of course, minimizing a loss function with respect to the parameters of the model. So WB is just a canonical notation that weights and biases. But more formally, it is just minimizing J theta over theta. So J theta is the loss function. So this loss function is denoted as J theta, and theta is the collection of all minimizing arguments or all learnable parameters, so to say. So WB as the theta, right? So for scalar theta, if we want to basically, I mean, we have all gone through this in 10+2, I mean, +2 or even +1. I don't know where it is. At our time, the minimum, maximum, minima were in +2. So we have all probably read this, that, okay, you take the first derivative and then equate it to 0. The other conditions, I'm not going into that, whether it's maxima and minima for double derivative and so on. But the way to basically solve it is that you basically take the derivative, equate it to 0, and then solve for the theta. So J is a function of theta, so it will be, this equation will be a function of theta, and try to solve, right? Now, this, if you translate it to multiple variables, that is a vector theta, not the scalar theta, then for high dimensional theta, the condition boils down to very similar, which is gradient of J. So grad J or nabla J with respect to theta is equal to 0 vector. So it is a bold face 0, right? So what that means is that this vector is equal to 0. And what that means in turn is that every of these partial derivatives will be equal to 0. So I mean, we see that we are translating it very well, that there was just one equation, one unknown. Here I think n equation and n unknown. So we can probably find it. If this allows us to find it, we will find it, right? But let us go ahead and see the complexity. Maybe this gives a very good, nice formulation, analytical solution. Mathematically we can find, but this is helpful but not always useful. So for example, J theta is this. So log of suppose, I mean, this is one of the functions. It's a sum of the exponentials where these a, b, theta, etc. are vectors. Is a convex function. I mean, if you plot this for I mean, we can only plot this for a two-dimensional theta, two-dimensional a, two-dimensional b. I have plotted this for some particular AB. I frankly don't remember what are the AB that I took, but I remember probably B was taken as 0. But anyway, if you plot this, you will find that it's a convex function. Convex is basically this bowl-shaped function. So in one dimensional, when I was drawing it, it was like this, but in 2 dimension, maybe it is like this. I mean, how can I draw? So this is the J theta axis, and say this is A and this is B. I frankly don't remember which was A and which was B. Sorry, theta 1 and theta 2. So theta 1 and theta 2 are the components of theta. So we see that there is a clear minima. But if you try to get an analytical solution of it, that is take gradient of J theta and basically equate it to 0. Well, I mean, it's not trivial. So if you do all these equations like the chain rule, etc., you will get this form. But it's a sum of exponential times the AI. So that is that is sum of the vector. So it may not be a trivial solution to find, if not impossible, right? So it may be very much intractable. So it's not easy to do this math and find the thetas, that is theta 1 and theta 2, that minimizes this, maybe somewhere here. Okay, so what can we do? What can be a naive way? if we can't say rely on the on our skill to solve an analytical problem, right? So it may give rise to lots of mistakes. So one naive thing is to basically take some thetas. So maybe here and evaluate. So what I'm trying to tell is these thetas, this and this. Sorry, I mean, I drew it again. Clear markings. So somewhere, okay, probably somewhere here, say, and maybe this is the corresponding j theta. So this is the theta 1, theta 2, this is the j theta. So then again, naively, I will randomly sample another one, say maybe here. Well, then, I mean, for the which the value is coming here, the j theta's value. So as I said, this is j theta. So it is not I mean, less than this value. So I'll discard it. So till now, this is my minima. Again, I will probably sample some value here, that is some theta here, and evaluate the j theta. So j theta, we know, right? This is the one. AB, we know, just the theta we are trying to find, which minimizes. So now we are assuming some theta, we are evaluating it. And in this way, we can hope that after some amount of such searching, we can find. Now, this may not be a very, very clever way. If we could have found, I mean, instead of this naive way and this analytical way, some in between. What is this in between? So the in between is that, okay, we will evaluate this j theta for different thetas, but we will intelligently try to make sure that we are going down in terms of j theta. So what, suppose I am computing it for some theta 0, which is a vector. This is a vector. So which has theta 1, which means that it has two components, theta 1, 0, theta 2, 0, right? So this theta 0 means the 0th value. First time this value, say this is the theta 0, right? So I'm computing and getting a j theta 0. Then whatever will be my theta 1, the next theta value, the value that I am getting of the loss function, j theta 1, this value should be lower than that. Similarly for theta 2, so j theta 2 will be lower than j theta 1. So I am moving constantly towards the minima. It's not that I am moving upward sometimes. So naive search will do that. So how can we do achieve this is given by gradient descent. As I said, I will take 10 minutes more. So maybe 110 I will leave, because we have lost so many times. So a numerical iterative solution is sought for. So as I said, start with an initial guess theta, repeatedly theta 0, repeatedly update theta by taking a small step. So this is the condition that we need to satisfy. So what this line basically means is that you get a new theta, which is theta k. So if k is, I mean, this theta k minus 1 basically is theta 0, then theta 1 is theta 0 plus, I'm saying that I will just part out this theta a little bit. So delta theta, note that it is not nabla theta, it is not this. It is delta, which is just small change in theta values. So what all the components will be changed a little bit. So that means this is a vector and this is a vector, right? So I am actually adding a small vector to one vector. So this vector gets added to here, right? So I am moving from one vector to another. That's what I mean by repeatedly update theta by taking a small step. Since I am moving, I'm taking a small step to move, right? And this small step is given by this delta theta, and the amount that, I mean, what generally happens is that this delta theta is generally unit vector. Sometimes we will see what exactly it is delta theta, we will see, but you can think for the purpose of understanding that this I have some if I yeah, let me just go ahead, go back to this slide. So I am at this theta 0. I will move, say, in this direction. So I can take this delta theta as a unit vector along this, and then how much I will move in that direction will come from eta, the length of the step that I am giving. So you can think that some human is walking, and this is the direction I have set. okay, you should work in this direction, and how much you should work, how much amount you should work is given by this eta, right? So this is what I mean when I tell that repeatedly update theta by taking a small step. I mean this. So theta, next theta is previous theta plus step size times some delta theta, some direction. Okay, so that this is important, so that j theta gets smaller with each update. So j theta k is less than equal to j theta k minus 1, and that is what I said here, right, in the last slide. J theta 0 will be less than j theta less than equal to j theta 0. J theta 2, this is, will be less than equal to j theta 1. See, this is translating to here that wherever I'm moving next, that should be less than equal to j theta k minus 1, right? Okay, so now let us try to see what will be a good theta, because if we know what will be a good theta, we are done, right? So we are intelligently searching. We don't have to rely on our skill to solve an analytical problem. Neither we have to depend on naive searching, right? So one implies what? So I'm just trying to find this delta theta, what will be a good delta theta. There may be many such, what can be a good one, or at least one of them. Let us see. So why I'm telling, so it's basically just I mean, this line basically puts theta k is theta k minus 1 plus eta delta theta. So this just tells basically I mean, puts this theta k value, nothing else. Now using Taylor series expansion, so I have explained the Taylor series expansion for multiple variables. So you are doing this, you can think that it is like j of x plus h, right? So jx plus h, sorry, I mean, this is a scalar, so this thus comes out, and then I mean theta, that is h transpose theta k minus 1. So if you just go back to the slide where I wrote that form, you will get it. So I hope I don't have to repeat it once more. So, and then some higher order terms. So this j theta k minus 1 plus this term is coming, neglecting the higher order term. So I have not yet used this equation 2. This is just using equation 1. So j theta k, just the theta k I have replaced. I have used Taylor series expansion, and ignoring the higher order terms, I have just made it approximately equal, right? Now let us go ahead and see what we are doing next. Now combining 2 and 3. By combining 2 and 3, what I mean is that, you see, just for the time being, again, since it is very much negligible terms, these higher order terms, you can think that these are equal. So this is saying that this j theta k, the left hand side, both has this j theta k. Equation 2 is saying that this is less than j theta k minus 1. And equation 3 is telling that this is equal to the same right hand side plus some term. So if you remove this term, this left hand side becomes less than the right, this first term in the right hand side. So what this means is that it must have be it has to be negative, this, otherwise this is not true. So just I'm giving you 10 seconds to think on that. Right? So if you remove it, so it is becoming, this side is becoming greater. So this must be negative. So that's what I have written. This must be negative. That is, this is negative because we have, okay, I have not told it. Yeah, I should have told it that eta is a positive value, small positive value, the step size. So the length. So eta is always a small positive value. So that I should have told it. So since eta is a small positive value, so that means this part is less than 0. Now tell me this, that what can be a good delta theta that will always make sure that when it is inner producted with this j prime theta k minus 1, it will be always negative. What can be a good delta theta? Can anybody tell?
Minus j dash theta k minus 1.
Yes, exactly. That's a very good choice. So for theta to minimize j theta, that is to satisfy 2, that is this, we have to choose some delta theta that is negative when a dot product of it is done with the gradient. I mean, that of course you have to disambiguate. That means the dot product is negative when a dot product is of it is done with the gradient of j prime theta k minus 1. So that's what I think somebody said it. I did not notice who said, and that's the problem with online class, right? I can't see your faces. So then why not choose delta theta as minus j prime theta k minus 1, and that actually gives you the gradient descent. So what is this j prime theta k minus 1? So j prime basically means this j this j theta evaluated at theta is equal to theta k minus 1, right? I think it was j theta and this was theta. Okay, so anyway, I mean this prime basically means the first derivative. So it is you are taking the derivative and you are moving in a direction which is negative to that, and that's what I mean. If you don't know anything about this proof or anything, if you know a little bit about gradient descent, that's what you know. That I mean, if you have coded any time gradient descent, that okay, I need to compute the gradient and then I need to move negative towards it. So that's how it is coming. And then I mean, it is just saying that if delta theta is this, then this times this is just negative of the norm square of the gradient, and surely this is a negative quantity because norm is always positive. Now, this is just one sort of a little simplified proof where this neglecting HOT is there, higher order terms. There are many complex proofs of these. I mean, from top of my mind, I don't remember, but something like two normals getting, I think, opposite, something like that. Yeah, but if you are interested, I can point you to one of the books. I think it is Chong and Jack. There is a optimization book. There you can get it. But yeah, I think this is just, at least intuitively, it is clear. Like in gradient descent, why we take negative of the gradient of theta. Any question?
Sir, why do we neglect the higher order terms?
Sorry, what? Why do we?
Why can we neglect the higher order terms?
Yeah, higher order terms you can neglect because this delta theta, when the quadratic term comes, which is like delta theta transpose j double prime theta k minus 1 and this delta theta, this quadratic term, this, I mean, if you just try to evaluate a quadratic term, you will see that the vector, the component of these, the square of these terms gets multiplied with the elements of these. So since these are very small, then you can basically ignore it. Now you can think it probably to convince yourself in terms of scalar. So if you think about this, it is like h squared, or I mean delta theta square if theta is scalar, j double prime theta k minus 1 divided by 2 or 2 factorial, then delta theta cube, it will come, right? So it will, I mean, we will move very small. I mean, this delta theta value will be small. That's why I said, when I said that you can think of it as an unit vector, but it is not an unit vector. It's just that a vector whose direction I need. Okay, it can very well work with a very big vector, but of course that will diverge in that case. It will not work. So if you take a very high delta theta or very high eta, you will get that, I mean, the gradient is this, suppose for, I mean, let me go ahead with the next slide. So this has this. So this is suppose the loss function that we want to minimize, and this is the theta 0 where we are starting. So the gradient is in this side, this direction. I will try to move here. Next times it comes to theta 1, theta 2, etc. And finally, probably with some tolerance, I'm reaching this minimization at theta equal to theta 3, whatever is that. Now, if you think that, okay, I mean, if suppose you are here and you are taking a long step, that means your gradient is in this side and you are taking a long step. That means, I mean, when you are taking a step, what happens? You are here, you are moving in this side. So when you are coming here, that means from here to here you have moved. right? Now, when you are say here, if you want to take a long step, you can actually go here. So it can diverge actually. If you can go here, you are missing the minimum. So that can be a problem if delta theta is high, and because then you cannot actually ignore the higher order terms. You can only ignore if delta theta is small. So as I said, these things, I mean, the proof that I given is a little simplified one. That's where this delta theta small is required. Even without using it, we can prove it using those other complex proofs that I frankly don't remember from top of my mind. Any other questions?
Sir, can we also say that since neta is very small, so for higher terms that neta
Yes.
square, neta cube will come?
Right. I missed that. Yes, because this eta is will also make this thing small. So this eta will also be squared, cubed, and so on. Right, you are right. So you can ignore. Yes. Any other questions?
Sir, why are we trying to minimize the loss function? Shouldn't we try to minimize the expectation of the loss function or something like that, sir?
Yes, you are right in thinking that. So the loss function, yeah, so that's why I think the last slide, you guys are actually going ahead. So the last slide, I forgot, I thought that was the last slide. So remember, in neural networks, the loss is computed by averaging the losses for all examples. Now, does it click anything, this word average and what you have used as expectation?
Yes,
right? You got it? So actually the loss that we are minimizing, it's actually the expectation of the losses, that is, but we approximate the expectation empirically by averaging. So we compute the losses for all the examples, then average it, and basically that is our loss. Now, since we have told this, I'm just taking your permission. Maybe can I take 2-3 minutes more? It will complete some small part then.
Yes, sir.
Yeah, okay. So this is the last slide. Actually 3 slides, but yeah, I mean, I'll try to just take, I also have to go somewhere, but yeah, I'm just trying to maximize the time that was lost. Okay. So now just coming from this, that remember in neural networks, the loss is computed by averaging the losses for all examples. So, but imagine this is a slide that is taken from NeuroIPS. Probably you guys know about NeuroIPS conference, Neural Information Processing System, one of the topmost machine learning conferences. NeuroIPS 18, after winning the Test of Time award for the NeuroIPS, or at that time it was called NIPS 2007 paper, the same conference. So that is by Olivier Bouquet and Leon Botou. So they actually basically got the Test of Time award. What is Test of Time award? So at that time, probably the paper was not kind of say well understood. I mean, I think the right word is not well understood, but the significance of it probably was not well received, well got by the community. But maybe after some time, people started to look into it and found the significance of it. So that such kind of papers get Test of Time award. So in 2018, these guys got it, and this is, so to say, as they say, started to kind of rekindle the I would say the popularity of stochastic gradient descent. So what we have told till now is gradient descent, and that has the relation of this thing, that in neural networks, the loss is computed by averaging the losses for all examples. But stochastic gradient descent, we will see that it basically takes this gradient update, that is this step after every example, and there is a in between where you don't neither take, or you neither take one single example, compute the gradient and take the step, nor you compute all the gradients for all the losses. If I don't know what I told, let me just rephrase. You neither compute losses for only single example, compute the gradient and take this step, nor you compute the losses for all the examples, take the sum of it, take the gradient, sum or average of it, take the gradient and take the step. You don't do anything of this, take in between. That is, you sample some examples, maybe 10, 12, 32, 64, which is called a batch size out of all the training examples. So then for all these examples, you compute the loss, you average, you compute the gradient, and then take this step. So that is called mini batch. So I'm just trying to give this idea in these 2-3 slides that how all these basically became popular. So stochastic gradient descent is the one, or as these guys told, is the online, at that time it was called online learning or online gradient descent, probably. The term online was there. It's like as and when you get one example, you compute the loss, compute the gradient, and do the update. That's the online sense, right? You don't have all of them together. So that is called the stochastic gradient descent or online gradient descent. So that was there in the literature from very early. But this is sort of the paper that probably rekindled it. I mean, they have some theoretical proof, etc. But I am just taking 2 slides from their talk. I mean, the talk link is there. It's probably a 12 to 15 minutes talk. Just watch this. It is a very good talk. So assume that your training set contains duplicates or 10 copies of, I mean, some duplicated copies of same examples. Now, if you now think that you are computing the loss for all these 100 same examples, or maybe just forget about it. Suppose you have 100 example and it is okay. Again, coming back. So 10 copies of 100 same examples. I am just taking say one such 100 example batch. Okay. Then if you are computing the loss for it, every of the example, you are just kind of wasting your computation, right? Because ultimately what you will do is you will take the average. So that average is same as single one. So this is one extreme case, but they kind of motivated from there. So instead, what you can do, you can compute the loss in one of the examples, take the gradient, and then you, compute the gradient and take the step. So your theta values have now changed. So for the same example, that is the second example, which is same, when you compute the j theta, now that the theta has changed, it will give you a different value of the gradient. So even if you don't compute the losses for all examples, you are moving towards the right value. So that is one extreme example. So they said that this motivated them to basically look into the stochastic gradient or the online gradient descent example more. So take advantage of the redundancy, etc. So it is stochastic gradient can be orders of magnitude faster. For such a kind of a scenario, but generally it is seen that it is also faster, and it is also in a sense more generalizable. What do I mean by this? This is another slide from their talk. They are saying that suppose you are starting with some W1. I have started always with theta 0 or W0. There is a historical reason why it is W1. I'm not going into that. Basically, it's a one-based indexing software that, computation software previously people were mostly using at that time, MATLAB. So, so if you do batch, that is you compute all the losses, average them, and then take the gradient, then you will straight away go to the base training set error. So what is that? When we told about basically the connection between deep learning and optimization, we told that in optimization, we try to find the minima or the minimizing argument of a loss function. But in machine learning, it asks more, that we hope that same parameter, same minimizing argument will also be a minimizer or minimizing argument for all the test examples, right? So these two can be different, but we hope that this is very close. I mean, this is the true solution, or just ignore true solution. This is the base generalization. Base generalization means it works based in the test set. That is, it generalizes well. Suppose that is W star and this is the WT star, that is which gives you the best training set minimization or least training set error. So when you do batch, they have shown it theoretically that I mean this is kind of known that you directly go to from optimization, you really go to this best training set error. Now when you do online or stochastic, one pass over examples, this you actually move in a separate trajectory, and that is kind of equidistant from as you move, it is equidistant from these two. So at least it can be closer to this base generalization. So I'm trying to just give the intuition. If you are interested, go into the paper, maybe there look into the proof and so on. I think they have actually published a book also, and several chapters are there also. So this is basically the thing that I wanted to tell. But one thing is that this can be slow. That is why slow, that will come next week. Just I think this is just the summary of the what I told in this. So mini batch, etc. So stochastic or online gradient descent is when you compute one single example's loss and compute the gradient. Batch is when you compute all the examples loss, average it, and compute the gradient and take the step. And mini batch is in between. So just the last slide. This is just kind of showing the difference between these three. So batch gradient descent, you have this learning rate epsilon k. So again, I have taken stuffs from different. So this is from again Subhendu Trivedi and Goodfellow, etc. So different sources. So I should have probably changed that eta to epsilon also, because next I have from this slide onwards it will be fully the deep learning book chapter 8. So I should have probably taken that eta as epsilon, but just take that step size eta as epsilon here. I've just used a different symbol here, but from now on it will be epsilon. So the learning rate or step size, it is called both ways, epsilon k. Initial parameter is theta, while stopping criteria do not. The stopping criteria is that when the loss function does not change a lot by changing the theta. That is a typical loss function. So compute gradient over all n examples. So you take the sum, average basically of the loss functions over all the examples, and then that is your gradient, and then theta minus epsilon, this g hat. Why g hat? Because this is not the true gradient, because we are just estimating using some n examples. It's not infinite number of examples, right? Stochastic gradient descent, just this line is different. Just you take everything is same, like learning rate, etc., etc. You just sample one example and then compute it, no summation, nothing is there, and then similarly apply update. What is a mini batch gradient descent? Sometimes it is called mini batch stochastic gradient descent also. Now, since this mini batch is so popular now, people say gradient descent, even stochastic gradient descent, but all mean this mini batch. So if nothing is called or specifically mentioned, you should take it as mini batch gradient descent. Now, again, same learning rate, theta, etc. same. Now, instead of sampling one example, you sample one mini batch of m examples, not n. M is less than n. And for this, you take the average of the loss, you compute the gradient, g hat, and you apply the update. So this is sort of, I could have probably stopped earlier, but I think this makes me feel good that the connected component, one connected component is completed. So if you have any questions, maybe 2 more minutes if you can spare, I can also spare. Any question on this part? Maybe from next time I should give one more lecture on this, because anyway I was hoping to complete this by this lecture. Last time it was done somehow. Anyway, if you don't have any questions, then I should end the meeting. The thing is that Piazza, etc., I have started slowly. So basically, Piazza enrollment is done. Just check in your mailboxes. The Moodle thing I will slowly start. This Tuesday I will be there in the office hours. And anything else? I think I'm forgetting something about the logistics. Yeah. One thing is that please do read the slide ahead a little bit. That will help. Okay. Thanks a lot. Thanks for giving that extra time to me. Thanks a lot.